Hello everyone. So I hope you're having a good ELC. So my name is Ian Rickards. I'm product guy from ARM in Cambridge in the UK. So I'm presenting on IPA, which is the Power Allocator Governor in the Linux thermal framework. So a bit of a mouthful, but basically this is an improved way of doing thermal control for consumer and embedded devices where you can passively cool the SoC using some features that we've upstreamed into the Linux kernel. Okay, so this is sort of interesting because ARM has traditionally worked within the sort of Arch ARM and Arch ARM64 parts of the Linux kernel, and now we're sort of diversifying a bit. We've got some guys that are working on thermal in fully open source within the Linux kernel. We're working on the energy-aware scheduling extension as well, which is being posted on LKML. So doing a few things outside the normal Arch ARM area. Okay, the guys that worked on this, actually I'm not a developer myself, but Javi, Puneet, KP at ARM worked on this and aided and abetted by the thermal maintainer, Eduardo Valentin. So thank you, the guys that did the real work. Okay, so just a bit of background. The existing Linux thermal framework, basically we have this kind of mechanism that evolved from kind of driving fans on CPUs and GPUs, but it's been kind of extended. So typically it has trip points associated with a cooling device. The cooling device was traditionally a fan, so trip 0 is typically a sort of turn-on point where the thermal solution becomes active. Trip 1 might be the sort of target temperature that you're aiming for. So originally designed for fans, but there's been a kind of extension to adjust CPU frequency. So the stepwise thermal governor basically will control CPU freak and kind of reduce the maximum frequency of your CPU to try to limit the power that your CPU is consuming. So actually, it's kind of clever. It's got, it looks at the direction the temperature's changing. So if the temperature's increasing, it tries to reduce the megahertz. If the temperature's going down, it will increase the megahertz. So some cleverness there, but so the power allocator is a significant improvement on that. So disadvantages with the current governors are they're kind of reactive. So they just wait until you go over the target temperature, and they just control the power to, say, the whole system, the CPU. They don't dynamically allocate the power between CPUs and GPUs. Okay, so typically used in mobile devices, we might see the thermal framework used. We might see some kind of custom firmware being run, either user space or maybe even a separate CPU in the system. Or we might see hot plugging. So hot plugging is used in some consumer devices where it's kind of a sledgehammer approach. If you've got a multi-core system, you just take out one of the CPUs that are running, wait for it to cool down a bit, then maybe reinsert it. But hot plug, of course, was designed for servers. It's not really designed for thermal control of consumer products. Okay, so IPA, the Intelligent Power Allocator, improves things in two main ways. So first of all, it's kind of proactive approach to thermal management. So it kind of uses a closed loop system where it looks at the difference between the current temperature and the target temperature and will moderate the power going into the system, so the SoC, to try to hit the target temperature and not exceed it. So kind of dynamically adjusts the power as you approach the target temperature. And it uses a PID algorithm. So I don't know if any of you guys did engineering. It's a kind of something you might learn in an engineering course. Proportional integral derivative control algorithm. So typically it might be used for accurate temperature control in an oven or pizza oven or something like that. But the same approach applies to an SOC, that you can accurately control the temperature into this system by using a kind of advanced algorithm to control the power. And so it's looking at basically the difference from the current temperature and the target temperature and the rate of change and the kind of thermal mass of the system. Okay. Another advancement with IPA is dynamic power allocation. So basically, instead of just controlling the whole SOC, we dynamically allocate power to the CPU or the GPU depending on the workload. So in mobile, you see a whole range of workloads between maybe compute intensive like benchmarks, or maybe some kind of intensive JavaScript on a web page, through to GPU intensive, where you've got some kind of virtual reality type scene. Okay, so IPA is able to do that. And IPA is merged upstream in Linux 4.2. So basically anything that derives from that, and we've got some backports as well. Okay, so how does it work? Well, we have the SoC, we have a temperature sensor on the SoC, on the die, so digital temperature sensor, very common piece of IP. In fact, your typical mobile SoC might have many of these digital temperature sensors. You might have a temperature sensor on the kind of motherboard for the device itself, so monitoring the sort of skin temperature of the device so that the phone or whatever it is doesn't get too warm. So that goes into the IPA algorithm in the Linux kernel. It's called Power Allocation&rdquo. IPA takes the performance requests from the different blocks in the system, so big cores, little cores, GPU. So basically that comes from the CPU Freak subsystem and the Dev Freak subsystem. So Dev Freak is kind of like CPU Freak, but for devices like GPUs. Okay, so we know from the frequency that CPU Freak is trying to run the cores at what performance is currently required by the workload. So typically, so for a graphics workload, you're going to see the GPU at a higher megahertz and the CPUs at lower megahertz, and the other way around for CPU-intensive workloads. So the power that's available in the system then gets divided up between the devices according to the workload requirements. Okay, and then there's basically this closed loop where the power will adapt based on the available thermal headroom. Okay, so just a quick piece of hardware background for you guys. So CMOS for dummies. So typically CMOS has a standard set of behaviors regarding power. So static power is like your leakage, and that depends on just the area of the silicon, so the area of each IP block. Depends on kind of the threshold voltage, which is one of the implementation decisions when you implement an SoC. So if you have a low VT, your transistors go faster, but they're more leaky. If you have high VT, transistors are a bit slower, but they're less leaky. So typically, you might use multiple VTs on a piece of silicon. The high-performance cores and the high-performance blocks will be low VT. The less performance critical and more power-saving blocks will be high VT. Okay. Dynamic power. So CMOS only uses power when it switches. So basically, it's the number of nodes that are swapping between high and low, and the capacitance. So, and actually, it's the square of the voltage is the power. So that's kind of illustrated there, and we've kind of plotted it against performance as well. So with performance, of course, you can increase the megahertz. The power is going to be kind of proportional to the megahertz, but because you've got dynamic voltage scaling as well, when you run at higher performance points, the voltage is going to be higher. Okay, so basically what we want to do is kind of optimize the power consumption of this kind of scenario. Okay, so requirements to use IPA, so really just a list here. So you need an on-chip temperature sensor. You need to be able to actually control your SoC blocks by adjusting the frequency and voltage. So if you can set the maximum frequency, that's going to reduce the power. If you can turn off CPUs, that's going to reduce the power. If you control the voltage, that's even better, because power is kind of the square of the voltage when you factor in frequency as well. So you need some kind of way of controlling the power going into the SoC. Okay, we need to write a power model of the SoC. So the IPA algorithm needs to have an accurate, well, fairly accurate power model, so that for each voltage point and megahertz point, and based on the utilization of that block, what's the power going to be? Okay, so basically this power model is able to translate between power consumption of the SoC and the performance cap. Okay, so it's not too difficult. So you can optionally write the static power model. The dynamic power model can be quite simple, and for the CPUs, we've kind of written one anyway. So it's just a matter of configuring the coefficients. Okay, so this is a kind of more technical view of how this might work. So we have the CPUs, we've got the power model. So the performance request comes in through CPU Freak, the performance metrics. The power model can specify the maximum power for that device, and then request a specific power based on the current workload. So basically, this all comes into the power allocator, and then it applies a policy and can allocate the power in your system between the workloads. Okay, so actually CPU, GPU, you could have other blocks in there. So say you've got a DSP, could even be something else in your system. Say that the battery charging circuit or the backlight uses a significant amount of power and is contributing to the power consumption of the device. You can control that as well. Okay, so this is a kind of stylized diagram of kind of the benefit of IPA, and we'll see this hopefully on the demo later, fingers crossed. So basically, with IPA, because it's able to really optimally control the power going into the system, we get a very fast ramp on the temperature up to the ideal operating temperature, and then it accurately stays at that temperature because it knows exactly the effect of changing the megahertz and changing the voltage. And it's using this PID algorithm to hit the target power. Okay, so it'll adapt basically to the system. So sometimes, like your consumer device, it even depends on like the orientation of it. If you've got it like on the sofa, there's going to be less power dissipation. If it's vertical in free air, you might have more power dissipation. So it will kind of adapt to that kind of environment. Okay, so that's on the left. On the right, we're kind of showing how the power allocated changes as the device heats up. So you can see on the left, there's kind of a lot of power to the GPU. That's the blue blocks, and less power to the CPUs because we're running a GPU-intensive workload. Then when the workload changes to a CPU-intensive workload, IPA will detect that through CPU Freak and Dev Freak and the graphics driver, and will reallocate the power to the CPUs and put the GPU at a lower operating point. Okay, so I won't go into all the technical detail. There's some configuration items that you need to do. There's DT, there's a sysfs implementation. So the things here are like the target temperature. You can have a weight for the device. So for instance, we can use the weight to reallocate power to the little cores instead of the big cores if we're under some kind of thermal limitation. We've got the parameters for the PID controller. That's the KPO, KPU, KI, etc. So too much detail for now, but there's white papers on this available. Okay, So this is configuring it in DT. Sorry about the small writing, but essentially what we've got here are 2 trip points. We've got trip point 0, which is this one, which is the turn-on point for the power allocator governor. So below that, everything is just at maximum. So when it turns on at 55 degrees C, then IPA becomes active in the kernel. And in this case, we've set the target temperature to 65 degrees C. So temperatures here are in millicelsius, because that's what the Linux kernel uses. Okay, and you can have different weights for the different devices. Okay, and you can override it in sysfs, so user space could change that. Okay, so IPA supports a thermal zone hierarchy as well. So what you can do is have a thermal zone for your SoC, which is a kind of rapid response zone that's limiting the power and temperature of the SoC, keeping the SoC within that operating temperature range. So that could be the big cores, the little cores, and the GPU. And the triangle here is the temperature sensor. And you could also have maybe a device thermal zone, which is your motherboard on your device. And you might have charging circuits and backlights that contribute to the temperature of that as well. So these can all be combined into a kind of hierarchy. And what will happen is the allocated power will be the minimum based on the different thermal zones you have. So it's able to control the SoC temperature and the motherboard device temperature. Okay, so a plot here of IPA running on a 4 big, 4 little core system. So what we're running here is Geekbench. So Geekbench is a CPU benchmark, and it kind of alternates between running a single-threaded test and then running a multi-threaded test. Okay, so obviously the multi-threaded test running 8 copies of some compute algorithm trying to run that on all 8 cores is going to use a lot of power. So what happens here, you'll see, so the device temperature is kind of sitting there nicely at the operating point. So it's not going over temperature. And what's happening is actually where we have these intensive periods of, so 400% load, which is all 4 cores running, actually IPA is pulling the frequency of the big cores down to a lower frequency. And if we compare that with the little cores, where the little cores are running at high frequency, at high utilization, so the high loads on the little cores correspond to high frequency operation. So this shows you that IPA is kind of reallocating the power to the little cores, and they're able to run at maximum performance, whereas the big cores are kind of limited. Okay, and that's sort of what you expect. The big cores are there for your single-threaded workloads or bursty workloads. They're not there for running continuous, compute-intensive workloads. Okay. Right, and we're introducing some support for capacities, so changing capacities on the big and little CPUs. So actually this is coming in as part of our work on energy-aware scheduling. So what happens is as you get capping in the system, it's possible that you could reduce the operating point of the big cores such that actually the little cores offer higher performance. And so in that case, what you want to do is kind of migrate tasks to the little cores. And so this is coming, we've got it in one of the ARM Git trees so far, and it will be posted in LKML in the very near future. So making the scheduler aware of this dynamic capacity changing of the CPUs and moving tasks across. Okay. For the future, we're going to be looking at hot plug. So this is a typical solution that people use to reduce the power in the system. And so you take out cores However, the hot plug mechanism is kind of overkill for this. You have to go through a long process taking the core down. So in fact, there's some proposals for sort of core idling, where you sort of temporarily idle cores rather than hot plug them. Okay, so something else for the future. Okay, so that's the summary of intelligent power allocation. So developed for upstream Linux, released in Linux 4.2. So basically, please, if you have kind of a system where you think there's going to be some kind of thermal limiting, then please consider IPA as a solution to that. And the results basically show accurate thermal control, better performance than the existing governors because of the dynamic power allocation. Okay, so in the future, we're looking at maybe core idling. We hope to perhaps combine the power model that IPA uses with the energy model that EAS uses into a single unified energy model. And so that will make things simpler. And EAS will be able to just accept the thermal budget given to it by IPA. So for instance, in a cold system, your thermal budget might be 2.5 watts. As the system heats up, it might go down to 1 watt or something. Okay, so I do have a quick demo. So let's see if this works. So I think I press a magic button here. Let's see. There are lots of green buttons here, so I'm probably pressing the wrong one. Is it swap or is it split screen? Take. Okay, right. Okay. The HDMI. Okay, actually, so it's mixing it, isn't it? Okay, so I have a demo here. Basically, I have an Odroid XU3 board you might be familiar with. So 4 Cortex-A15s, 4 Cortex-A7s. It's got thermal sensors. It shows some interesting kind of thermal properties. So when you run the GPU intensively, when you run the big cores intensively, it heats up. So it's a great kind of board for evaluating this. It was swap that I pressed. So looks like I pressed the wrong button. Ah, right. Okay. Yeah, please, fire away.
So, I guess the challenge with closed loop governors is tuning them. You have these loop constants that sometimes need to be changed to tune the given system. Is there any tool or documentation with the governor that helps you tune the constants for the PID?
Right. So we're basically working on some PDF documentation that's going to tell you all of this. It's not quite finished yet. So there's an IPA technical presentation on the ARM website. In the Linux docs directory, there's documentation as well. But you're right, the thermal coefficients are something that you kind of just have to measure and test. There's no way of magically running a program that will determine this. I wouldn't say we've noticed that, but yeah. So the current draw, so the power supply, the quality of the power supply, as the current increases, the voltage is going to vary. Right, yes, yes. Right, so we typically haven't done that. I think we've assumed that there's power available at the necessary level. And so what you could do, if you know that your battery's draining, you could change the sustainable power point, so reduce that as you know that there's less power available from the battery. You could do that, and that's going to limit the power into the system. Right, it's not built in, no. Okay. So the question was, if I get this right, as your battery runs down on the mobile, the question is how much power can be supplied because at the lower voltages of the battery, the current available is lower. So I think we can accommodate that because you can control the power, basically. So you could have some daemon which is monitoring the battery and limiting the max power. So even if you're not thermally constrained, you can limit the power. Right, so we've got this kind of summary slide mixed in the middle of it. So the background screen is okay, but we've got a bit of a mix going on.
So, as far as I kind of understand, you add thermal zones, and can you add any thermal zones? So basically, like, what I care most about would be the skin temperature rather than the actual CPU.
Right. So you could do that. So a device might decide that actually the SoC, you don't need to worry about that. If it's the skin temperature, you can have a thermal zone for just the device with a temperature sensor on the motherboard. And you know the heat sources that contribute to that, you can model that as well.
Could you talk a little bit more about how the governor allocates power between, say, the CPU and the GPU, for example?
Right, so it basically takes the power budget, it takes the performance requests, and then allocates it according to a weight. So the weight will basically favor, so say you might have a higher weight for the little cores to favor the little cores when you're allocating power. And then, so it basically is according to the performance request.
That's reported, I guess, from the GPU.
Right, exactly. And CPU Freak is telling you the performance request for the CPUs. We've got all kinds of effects here. So actually, if you guys don't mind seeing it just on half the screen, that might work. We could make the other one, yeah. Oh. This is the most entertaining presentation, isn't it, by far? It's always good when the demo doesn't quite work.
Here's another question for you.
Excellent.
So, in a lot of GPUs, they do a fair amount of computation in the CPU driver to submit data to the GPU. Is the intelligent power allocator handle that kind of ping-ponging between the CPU time and, say, the GPU driver versus GPU time?
Actually, no, so it doesn't. It's just, because that would happen maybe within a vsync period. You'd have a CPU-intensive period, then a GPU-intensive period, maybe in a game. So It's not, this isn't it. This is my little webcam for showing you what's on the table here, because, and you can see the buttons here as well. It is actually quite complicated. So I've got an Odroid XU3 board, I've got a touch screen, it's running Android, I've got a touch screen, I've got a Chromebook, which is running a kind of Debian to control the system. So, okay. Okay, well, this might have to be a verbal demo, so. Okay, excellent. Oh, right. Okay, right. Okay, right. I can get something on that. Right. Let's move that to the other screen. Right. Okay. Thank you. Right. Okay. Let's. Okay. So what I have here is a monitor that is running on the target, looking at some of the values in these sysfs locations, reporting the temperature of the system. So on the touch screen here, so you can't see it, and I guess it may be too, well, so if I press take, you think it might change? Okay. Okay, no, it's going between something that's been captured previously. So the demo I'm going to run here is, so basically it's running Android. Okay, so I've got Android running here. I'm going to run Ice Cave, which is an ARM GPU demo. Okay, and it's very GPU intensive. So once it's loaded up, basically, you'll see all kinds of fancy lighting effects, thanks to the Enlighten technology in Mali. And so if I swap back to this, you can basically see the device is heating up because it's in pretty intensive demo. And I have an extra helper here in terms of a hairdryer. So, because it is an ARM system, so it needs a helping hand. So basically what I'm going to do, so you can see the temperature is basically getting close to the target temperature, and maybe the power is being reduced a bit, but if I heat it up a bit more, basically what you can do is you'll see IPA adapt to it. So actually the gap there is actually where IPA has gone off because it dropped below the trip 0 point. Okay, so now the hairdryer is having an effect. The temperature's getting near the target temperature. It's reducing the power, but because it's a GPU workload, the power is being kept up to the GPU, and the blue and the green are the big cores and the little cores, so the power is being reduced to the big and little cores. Okay, and if I continue to heat it up, you eventually will see that the GPU gets capped as well. Ah, right. Okay, it's going, right, yeah. Okay, but the nice thing is, even with the added heat, we're still not exceeding the target temperature. Right, okay, so there's a fan running on the, right, because the fan actually helps the demo in this case. So, because it will help it get up to, when I blow the hot air at it, it pulls the hot air in. So for this part of the demo, it's working. So what I'm going to do now is try a different demo. So we'll swap to a different benchmark. Actually, one thing I should have shown you was that the frames per second also, let's see if this works. So there's a kind of frames per second. So it's 30 frames per second, and even as even as I heat it, it doesn't really drop. Because it's capping the power to the CPUs, and they're not really part of the demo. Okay, right. So if I stop this, okay, we'll now swap to so I'll now swap to a different demo. Okay, so I'll turn off the fan, 744, and then I will run. So we've got a framework for running benchmarks here. So, so the 778 is going to run Antutu. So this is kind of remotely running Antutu on the target. So Antutu is going to start up and go through various different phases. Oh, right, Antutu. Okay, and so I don't know if people have run Antutu. It runs various different phases. There's kind of a CPU test. There's a single-threaded test, a multi-threaded test, graphics test. And it's interesting to look at the workload as you're running the test. So if I go back to the... So basically, to start with, it's saying... right, okay, so the test is actually now starting running because it's simulating mouse clicks. So it's testing runtime performance, single-thread integer performance. Okay, so this is going to be lighting up like one CPU, not going to be using that much power. Okay, so the temperature is only rising slowly. So single-threaded performance. Okay, so it's swapping to float performance now. Okay, and the fan is off on this device, so it's heating up, and as a result, it's reaching the target temperature, the power's being capped, but because it's a CPU workload, you can see the GPU power's being capped, the CPU power is being kept up, and single-threaded, so the blue cores, which are the big cores, are getting the power. Right. It says testing CPU integer performance now. Okay, so because there is no cooling, it's basically significantly limiting the operating point on the CPUs. Okay, so this is some kind of multi-threaded test. You can see that the big cores are all lit up, so quite an intensive benchmark. Okay, and then at different phases, so it's saying testing RAM performance now. It actually still seems to be CPU intensive at this point. Okay, and now it's dropped off. So interestingly, it's reporting testing multitask performance, but the temperature's recovering and the power's increasing. Okay, and then just at the end of Antutu, there's a graphics demo. So we'll see the power allocation swap. So there are two graphics demos. There's a 2D graphics demo that's not very CPU intensive, and there's a not very GPU intensive, and then there's a 3D graphics demo that's more intensive. So, okay, so this is the 2D demo. So if I swap back, you can see that actually the temperature's dropping and IPA's switched off, which is why all the power allocation has gone to 0, because it's dropped below the turn-on point. So everything's getting its full allocation of frequency. It's still doing a GPU demo, a 2D GPU demo. Right, so now it's loading a 3D demo, and temperature increases, and the power is allocated to the GPU because it's a GPU workload. Okay, and because the fan isn't on, the device is heating up, so the power has to be reduced. Okay, and just to prove it's the 3D demo, there you are. Excellent. Okay, well, so that's the end of the demo. So thank you all very much. So please, if you have any further questions, come up and ask me, or go away and implement intelligent power allocation in your devices. What tool is this? Okay, so this is actually just JavaScript in a web browser. It's basically just reading the status files out of the XU3 and displaying it on the Chromebook. So it's just a little bit of JavaScript. Okay, so actually I think this kind of ties into the sort of energy-aware scheduling discussion, and there's CPU freak, there's shed freak, there's some p-state stuff going on. So so in fact, the people that you need to talk to on that are actually sitting behind you. So, probably not a question for me. So any other questions? Okay, thank you very much. Thanks.